Incremental potential contact, or IPC, is the state-of-the-art for simulating intersection and inversion-free updates using implicit integration. However, devising a high-performance IPC implementation with fast convergence as promised by Newton-type solvers remains a challenge due to the indefiniteness of the original IPC barrier Hessian, potential numerical problems, and the inefficiency of the linear solver. We propose a novel GPU Gauss-Newton optimization of IPC to resolve these problems. Our approach is based on a rewriting of the barrier function to derive analytic expressions for the eigensystem of its approximate Hessian that allow fast projection to positive semidefinite state. We rewrite the barrier function using a novel expression of the gap function that we use to measure contact distance. This gap function is evaluated with a local contact constraint Jacobian and normal vector, from which the expressions for our barrier gradient and Hessian are derived. This constraint Jacobian is evaluated from vertices in the stencil of a local contact, where we show a unique construction, reducing it to a diagonal matrix. To handle the notorious case of nearly parallel edges, we also present a novel modified barrier function expressed in terms of the constraint Jacobian, where we provide analytic eigensystems of its approximate Hessian for fast and robust minimization. Moreover, our analysis yields tangential component-free solutions, unlike the distance-based formulation of Lee et al. 2020. These tangential components in the solution vector have the effect of introducing subtle, but undesirable deviations of simulation trajectories over time. Our eigensystems provide up to 3 times speed-up over standard IPC, which is significant given that a few minutes' worth of simulation time will typically require tens of hours to compute, and that we obtain visually matching results. Evaluating the original barrier function at extremely small distance scales also poses several numerical challenges for IPC solvers due to vanishing displacements, which we address by filtering eigenvalues prior to solving the linear system and elevating the barrier profile by steepening its gradient. Here we show another example comparing the solutions computed using standard IPC, the Gauss-Newton method of Lee 2020, and our formulation with filtering added. We also present a massively parallel GPU IPC implementation with carefully designed PCG solver. Our GPU IPC framework is over 95 times faster than standard IPC running on the CPU. Our eigensystems provide up to 3 times speed-up compared to a hybrid GPU and CPU framework where the positive semidefinite projection of the Hessian is numerically done on the CPU with the eigen library. Here we reproduce the stress test of Lee et al. With extreme twisting of a volumetric mat for 100 seconds and a comparison of performance with Lee et al. For the first 50 seconds. Our method successively simulates the twist under high pressure. We also reproduce the rod twisting test, which runs for 100 seconds, and also compare the performance with Lee et al. For the first 50 seconds. Our method is able to efficiently capture the stretching contacts and buckling effects. Our method likewise works on intricate geometries as shown here. A comparison with medial IPC also shows that our method is faster and offers a simulator with non-penetration guarantees. Here we show a simulation involving a soft body with cloth interaction, which also involves frictional contact. And also our ability to simulate frictional contact with different coefficients. We simulate a card house with stiff boards and impact the house with a dropping block. We keep the house shape with static frictional contact between the boards. Our method is robust to varying time step sizes. The simulation remains both intersection and inversion-free throughout. Gauss-Newton optimization of IPC on materials with varying stiffness is known to be extremely challenging. Here we show that our approach can robustly simulate both soft and near-rigid elastic materials, and with faster convergence rates than standard IPC. Our method achieves the most efficient Newton-Solver convergence rates, especially with a high accuracy tolerance. In contrast, existing Gauss-Newton methods have low convergence rates and may even fail with high accuracy tolerance thresholds to highlight the significance of our approach. Here we compare visual results with the standard IPC framework. The models shaded in green denote simulation results computed with standard IPC, while the models in orange are those computed by our method. Despite the barrier Hessian approximations, our system produces practically identical results. And our method passes all these unit test cases. Here we show an example where we use our method for simulating multilayered cloth, which runs in approximately 2.5 seconds per frame with frictional contacts. Furthermore, our approach is capable of managing increasingly complex cloth simulations involving frictional contact. The effective modeling of friction ensures that the dress remains accurately positioned on the body throughout the simulation. Finally, our simulator is also fully differentiable. In this example, we start from the blue dress to then optimize its stretch stiffness parameter such that the draped motion matches that of the reference dress in orange. While there is still room for further exploration of differentiable simulation techniques, our method brings notable performance advantages to the field.